Welcome back after lunch. So the next speaker is Pei Wu, and he's going to tell us about an optimal it ain't over until it's over theorem. So take it away, Pei.
Thank you. Good afternoon. And okay, so let's see what is this it ain't over till it's over theorem. And this is a joint work with Rona Alden and Javi Victorson. Okay. Sorry, maybe you probably already know this background, but let's still review it very quickly. And all starts, this talk is about Boolean function analysis. So we first review this notion of influences. I think in the morning, Dan already set up for me. So here we have a Boolean function. And the influence of individual variable is just the probability that you flip this variable xi so that you flip the value of your function over a uniformly random input over the Boolean cube. And the max influence is just a maximum over all the individual influences. Okay. And here are some examples. The first one is the majority function. This example actually matters for our results. So let's see. The majority function simply outputs the majority bit of its inputs. And the max influence of the majority function is 1 over square root of n. The reason is simple because for any bit to be sensitive, meaning if you flip that bit, you flip the value of a function, it has to be the case that in your input, there are approximately equal number of 0 and 1s. Like in this case, 0, 1, 0, 1, 0. You flip 0, you flip the majority bit. And also, like, the probability over uniformly random inputs that you have approximately equal number of 0 and 1s is 1 over square root of n. And the conditioning on that event, any bit is sensitive with constant probability. Therefore, the max influence of the majority function is 1 over square root of n. Maybe any questions about the definition? Okay. Good. And the second example is the so-called tribes function. You have this and composed with or, and the panning is set so that it outputs 0 and 1 with approximately equal probability. In particular, the panning to the AND gate is n over log n, and the panning to the OR function is about log n minus log n. So you can also calculate the max influence of the tribes function is log n over n. So this is maybe an exercise for you. So in this talk, we will be interested in such functions, namely the functions whose max influences is very small. Like in the previous examples, they are polynomially small. And also, we will say that for simplicity, let's just say that these functions output 0 and 1 with about equal probability of uniformly random inputs, and we call such function balanced function. So if this is the first time that you see these kind of functions, it's a little bit weird. But there are many motivations. For example, they shows up naturally in social choice theory. So I guess maybe on Friday we have the happy hour. Somebody prefers to go to Oakland and somebody prefers to stay in Berkeley. So you have to make a decision, and you aggregate your opinion and maybe use the majority vote to decide where to go. And there are like more complicated situations, and you want to design more complicated aggregation function. Like when we elect the president, maybe we have this majority composed with majority kind of function. This, in many situations, what we would want to, what the property that we would want to have for this kind of aggregation function is that no individual should be able to determine the outcome regardless of other people's opinion. And this is kind of captured by max influence being small. And the second motivation comes from the study of hardness approximation. So we know there is this dictatorship test. You want to distinguish a dictator function, meaning individual bits determine the output of your function, or functions far away from dictatorship function. That's functions whose max influence is small. And maybe a third reason these kind of functions are interesting is because of this invariance principle. A typical example is the central limit theorem. So if you want to take a sum of independent -1 + 1 random variables, no variable that kind of dominates the output. Therefore, you can actually replace these Boolean valued random variables with Gaussian random variables. And the sum of Gaussian random variables is a Gaussian. Okay. So in this talk, we were just studying the random restrictions on such functions. So functions with small individual influences. Maybe for concreteness, let's just say in this talk, we want to study the random restriction such that you fix exactly p times n number of random bits. And you can also think of random restriction that fix input with independent probability p. That's also fine. Okay. So maybe any questions at this point? Okay. So what we proved, it's also this the so-called it n over till it's over theorem, is that for any function that its max influence is small, then we can actually restrict all but 1 over log 1 over the max influence fraction of the inputs. And what will happen is we show that the restricted function will remain nonconstant with high probability if the original function is balanced. Okay, so recall that for majority function and tribes function, the max influence is polynomially small. So it's kind of saying that you can restrict, for those kind of function, you can restrict all but 1 over log and fraction of the inputs. And now this already tells you that this theorem is optimal with respect to this allowed probability, because for the tribes function, it adapts to AC0 circuits. Therefore, using hashtag switching lemma, if you set the allowed probability to be order of 1 over log n, you are going to get a constant function with high probability. You can also calculate this probability on your own. And another thing I want to mention is that here I only say, okay, this restrict function is non-constant, but actually you can also say how non-constant it is. So you have this notion of variance, and it's kind of saying, okay, even after the restriction, your restricted function will be somewhat balanced. And this matches the behavior of the majority function. So in this sense, we give a tight analysis on the behavior of the variance. Okay. Any question about the?
Also have the other direction.
Wait, what is the other?
Probability of variance.
Yeah. No. Oh, okay. Yes. I mean, like, yes. By the other direction, I mean the majority function behaves like the other direction. Yeah. Okay. So maybe more comments is this very cool name, it n over till it's over, is actually contributed by Friedgut and Kalai. So in the study of social choice theory, we will see this application later. They're interested in the case where the allowed probability is a constant, a very small constant. Here, we definitely go beyond that. We can be a little O1. And also, the original conjecture was proved already by Mossel, and Oleszkiewicz. But their result is suboptimal. So this is nice. And also, I heard that Kohler, Lipschitz, Minzer, and Mossel, they have a different proof. So maybe at some point they will teach us. So okay, maybe before I move to applications, any questions? Okay.
Even neither shoot us.
Oh, okay. I hope that you don't ask. Yes, yes. So, so like as I said, for example, if you consider the tribes function, you need to keep the to get a constant function, you need to get like the lie probability to be order of 1/log n. And here, what we get is like log n over log n. So, so in between, we don't know how to analyze. Okay. So maybe now let's move to the applications. The first one is about block sensitivity. It's actually our original motivation to study this problem. So using this result, we can show that if your function is balanced and with small influences, then the block sensitivity on the random input will be at least log 1 over the max influence, almost surely. Okay, so just maybe to remind you what's sensitivity and block sensitivity. Sensitivity is just that on any input x, it's just a number of bits that you can flip to flip the value of function. And the block sensitivity is just the number of disjoint blocks of variables that you can flip to flip the value of function. So block sensitivity is clearly larger than sensitivity. Sorry, okay, say it again. No, yeah, that's the next line. We don't expect such results for sensitivity just because of the majority function. Okay, because the majority function for most of the inputs, their sensitivity is 0. And also another thing I want to comment is that just using the KKL inequality, you know that the average sensitivity is at least log 1 over the max influence. Therefore, the average block sensitivity is also at least log 1 over the max influences. And we are kind of saying that the average is large because for block sensitivity, it is because every input has large block sensitivity. Okay. Maybe let's see how this is proved. So we just take a random input and you partition it into random blocks of suitable number of blocks. And now for any fixed block, if you look at this input x and the other blocks, then that actually gives you a random restriction. And by our theorem, this part is non-constant. This restrictive function is non-constant with high probability. Therefore, within this block, you can flip something to get a different value. So within this block, there is a sensitive block. And basically, then you can show that with high probability, a lot of these blocks contains a sensitive block. Okay, so that's the first application. And so here it kind of uses the fact that our result about the lie probability is optimal. And the next application, maybe let's see why we want to understand the variance, not just that the restrictive function is non-constant. So this application comes from the social choice theory. So we know, that we have if we have two candidates, blue and red, and we want to, maybe I prefer blue over red. So this is me. One just indicates that my preference is blue greater than red. And now within this room, maybe people have different opinions. So we just put it in this array. And to aggregate our opinion, we can apply any function f. And we say that if we say that we prefer maybe the blue if this function gives us 1 on this array. Okay, so this is the case when we have only 2 candidates and not much to say. But it becomes more complicated when we have more than 2 candidates. When we have 3 candidates, the question is how we aggregate our opinion. And the story is, I guess, Condorcet and their friends, I guess, they were trying to come up with a voting scheme to elect members for French Academy of Science. So a quite serious situation. And Condorcet just proposed this method that, okay, let's just apply maybe F on different arrays of these numbers, and let's see how they aggregate. And the hope is that we get something meaningful, like here, maybe as a group, we prefer green than blue and red, and blue is greater than red. But you can think about it, it's not necessarily the case that it always comes out this kind of rational outcome. You can get a circle. Okay. So let's just call this Condorcet profile as the outcome. And we want to just say, okay, so let's say we have this function that's fair in the sense that it's a balanced function. So the 2 voters have equal chance to win. And also this function has small max influences. Then let's make like a little bit more assumptions. Otherwise, we can't really say anything. The more assumption is we are going to say, okay, the voters' preferences are uniformly at random over all the rational or over all the total ordering of these candidates. And then we can prove that any Condorcet profile will happen with constant probability. So any irrational outcome can happen with a constant probability. Okay, so for case, okay, so the approach we're generalizes for k greater than 3, your C. Maybe any questions about the statement of the theorem?
When you say any Condorcet profile, you mean the
No, I mean the I give you this graph, directed graph. Like you can put any direction on these edges. The Condorcet profile is just impossible ways.
where this would be 8 options.
Yeah.
It's not the 6.
Oh,
The 6 legal ones.
yeah, 6 are the legal ones. Yes.
So if it's like a more k for large, k is a still constant. Oh,
So it seems that you always predict what I'm going to say. Yeah, so for larger k, I mean like we can't do all k, but for some small k, we can show for our approach, what we get is exponential decay. And I don't expect this to be the right answer. So this is open for you. Okay. So maybe let's just see the proof. So what we are going to do is we are going to partition the voters into 3 groups. It's random partition. So I belong to the first group or second group or third group with probably 1/3. And then what I'm going to do is for the first group, I only ask them what's their opinion on red versus green, green versus blue. And for the second group, I'll only ask them what's their opinion on blue versus red, red versus green, and etc. And then we should notice that with these, so for me, for example, if I give these two opinions, then with a constant probability that I cannot differ what is my opinion on blue versus red, right? And for the other thing, maybe I can differ. Maybe I can differ what, given, for example, I know red is greater than green, green is greater than blue, then I know, okay, red is greater than blue. So that is inferred, that's fixed. And for the all entries, that's not fixed. And all the entries that's fixed, it gives us a random restriction. So now the total probability of the total probability of this restricted probability you can calculate is a constant. And therefore we can apply our theorem and show that the restricted function is non-constant. And in addition, the variance is very large, it's balanced. So now just notice that for these three different kinds of columns, they are independent. So we can show, okay, for any possible outcome with this constant probability, it will show up. Any questions? Okay. Good. So if you are interested, there are like a lot more. You can find, in particular, Mossel has this survey. So now maybe let's return to our main result and see what happened there. So maybe just recall what we proved. So we want to study random restrictions on Boolean functions such that their max influences is small. And our strategy is to study some random processes and relate that random process with this problem we are interested in. Okay, so let's start with simple. Let's start with some setup and the most simple random process. The setup is that we are going to think our input is encoded by -1 and 1. This is because we want to go beyond the Boolean cube, or maybe go inside the Boolean cube. So we will think that this function not just evaluates for Boolean valued inputs, but also for any real value inputs by considering its multilinear extension. And now the basic random process we are going to study is this uniform process. In particular, we're just going to expose the variables in a random order. And in the beginning, when we know nothing about these inputs, we just let them to be 0. And each time we expose a variable, so maybe in the first time we expose this variable, and in second time maybe we expose another variable. So we will only use like 0, 1, -1. This is like the minimum possible way to go inside the Boolean cube. Okay. And also when we expose a variable, it's going to be set 1 or -1 with equal probability. So is this process clear? Any questions? Okay. Now maybe let's just make some simple observations about this process. So first, at time t, you expose t variables. So it kind of induces a random restriction with t variables fixed. And at time n, you get a uniformly random element from your Boolean cube. And another thing that's relevant to us is the influence of a function. It's just the partial derivative at the end point squared. I mean, this is because the individual influence of the variable xi is the probability you flip your function by flipping this variable. And partial derivative with respect to this function at variable I is also flipping this variable because it's a multilinear function. So flipping this variable and see if it changes or not. Okay. And maybe the fourth observation is that consider this time t running from 0, 1, 2, and evaluated at our function f. Then what we get is a martingale. This is also a simple fact from multilinearity of our function f. Okay.
Sure. What does f evaluated at xt is? Xt is partial, isn't complete.
Yeah. I mean, okay. So when we not restrict this input bit, we put 0 there.
But we have -1, 0, and 1.
Yes. And we can evaluate it because we are going to treat it as a multilinear function.
0 is like a random.
Yeah.
I see. Okay.
Okay. So that's the most basic random processes. And next we are going to modify it a little bit. In particular, when we expose a variable, now we don't set them to be +1 or -1 with equal probability. We are going to choose a probability such that in the end, we actually sample uniformly random element that's from the pre-image of 1 for this function f. And in fact, in each step, we choose 1 or -1 based on like the restricted. We look at the restricted subcube and see how much ones is inside them. And the probability distribution is set to be proportional to the density of each of the subcube. So maybe I want to mention one more property of this process. Is that suppose we fix any pass. By pass, I mean like in the beginning, we have no information. At time 1, we fix some variable. At time 2, we fix some other variables. And at time t, so this entire pass. This is what I mean by pass. So fix any such pass. The probability our second, the conditional process follow this pass. If we compare it with the probability that a uniform process follow this pass, it's going to be f evaluated at the endpoint divided by f0. I mean, intuitively, it's just saying our conditional process has this bias towards going to 1. So whenever this subcube has more ones, it has higher probability go to that subcube. And whenever that subcube has less ones, it has this conditional process has less probability to go inside that subcube. That's all it's saying. So next,
explain the process a bit more, like how do you get?
Okay, sure, definitely. So our goal is making sure that this process end up in a uniformly random element whose evaluation on f is 1. And in particular, what we're going to do is, okay, if we are exposed this variable, if we set it to 1, we get a restricted subcube. And inside this subcube, there is maybe this number of ones. And if we set this variable to be -1, then within another subcube, then maybe we have a different number of ones. We just want to set the probability to be proportional to the number of ones in this subcube and this subcube.
X. This picture is described Y, but in the bottom we have X.
Okay, then sorry, maybe it should be Y. All right, thank you. So I guess here maybe it's also here it doesn't matter. Okay, maybe any more questions?
Just a step size. It's still a margin gap, but just a step size.
No, it's not. Y is not a margin gap. Okay. So now we will change our perspective. So we studied this so-called control process. It's going to be a bridge to connect our theorem and the random process we discussed so far. So in particular, we are going to study the following game. Still, we are going to expose the variables in a random order. But now with probability, with a large probability, we're going to expose the variable uniformly at random. And with the remaining probability, we are going to let the player, you, to decide how to set the value for these variables. And your goal is to sample a pre-image of 1 uniformly at random for this function f. Okay, and here I just want to say, okay, if you think about it, if in the end of this process, you don't have control, then you basically lose automatically. So we give more freedom to the player. We set some time that's close enough to the end point. And we just say, okay, after this time, you do whatever you want. And now our goal is to show, okay, after this modification, then as a player, you can actually win this game. So let's see how this is related to our theorem first. This is just because if we look at these points that's not controlled by you, it's exposed at random, then that gives you a random restriction. And what you are doing, what you can do is you can just sample a uniformly random input with value 1 on the function f. And now we can also say, okay, we just study 1 minus f. And we will say the same thing. For 1 minus f, you can also sample a pre-image of 1. That is, you set these variables to be 0. So all in all, I'm saying that as a player, if you can sample uniform random pre-image of 1, then you can in fact set these restricted blocks such that you get either 0 or 1. So that's not a constant. And the probability to sample will help us to analyze the variance of the restricted function. But that's not what we need to worry. Okay. Is this clear? Okay. Yeah, so this is how it's connected to our theorem. And next, I guess it's more straightforward how this control process is related to the previous random processes. That is, we are going to ask the player to implement the strategy that is to just simulate the conditioned process. So whenever the player get a chance to play, what he should do is try to set the probability distribution of setting +1 minus -1 in a way so that in the end, this distribution is the same as the distribution of the conditioned process. And if you set this goal, you can actually calculate what are these numbers. And it's going to be like half plus minus the partial derivative of function with respect to the variable to expose at this point, divided by 2 times epsilon times the value of function evaluated at this point. And this epsilon is used to compensate for the fact that you only have epsilon probability to play. Anyway, so this is just some straightforward calculation. And the thing is, for this to be a valid probability distribution, it has to be the case that the partial derivatives is much smaller than like epsilon times the value of a function. So therefore, our goal is actually to study when this condition is going to be violated. And for technical reason, we are going to just to consider two subcases. Maybe the first case is when the partial derivative becomes too large, any of the partial derivative becomes too large, or the value of function become too small. So if neither of these things happens, then the value of function will be much larger than the partial derivative. And here, like I said, the epsilon delta doesn't matter. It's just some placeholder. Any question?
So is it like if this inequality in the fact doesn't hold, then we?
Yeah. Okay. So the player's strategy is to choose some probability distribution so that the player, as a total effect, can simulate the conditional process. But for this strategy to be valid, it has to be the case that this number is a valid distribution. And so if this thing becomes greater than 1, then it doesn't make sense for probability distribution.
In that case, are we saying there is no way the player, or it's just this specific strategy?
Yeah, this strategy fails. But I'm going to say that what I want to say is that this thing will not fail because we set this time to be a little bit ahead of the endpoint. Okay. Any other questions? Okay. So our goal is to analyze when like our conditions does not hold. And in particular, we consider two cases. The first case is when the partial derivative become too large. And the second condition is when the value of the function become too small. So as long as we can show that this thing does not happen very early, then we are fine. The player can implement this strategy. And that is our goal. Okay. So let's just look at these two situations one by one. The first one is when the value of function become too small. And this is actually easy to show. And just maybe just recall that our conditional process has these preferences towards like larger subcubes. And in particular, recall that I said, if you have this pass that goes to some subcube that is very tiny, then our conditional process follow that pass divided by the uniform process follow that pass is at most like the endpoint divided by F0. And endpoint is very, very tiny. So this thing is upper bounded by a very tiny quantity. So the probability that your conditional process go into a subcube with very small value is very, very tiny. So this is the easy case. And the second case is we want to understand when our partial derivative become too large. And recall that partial derivative is related to the influence. That's where kind of we are going to use the max influence is small. So again, we are going to use the fact that our conditional process, in some sense, is not too far away from the uniform process. So in particular, I claim that we only need to bound the probability that on uniform random process, what's the probability that the partial derivative become too large? This is again just using the fact that these two probability measure differs by a factor of at most f evaluated at your current point divided by f0, and that is at most 1. And the f0 is some constant, so we can ignore this part. We just need to analyze the probability that our uniform process will hit some point where this partial derivative become too large in an early point. So here, maybe I apologize that we need to switch a little bit from a discrete process to a continuous process in the following sense. This is basically for technical reason. If you don't care, you can just think it as a discrete process. So in particular, now we no longer have this discrete time 0, 1 till n, but we have this continuous time, the unit interval. And then for each variable, we are going to just sample a time point, timestamp from this unit interval. And what we do is we run our process from time 0 to time 1. And when we hit a time stamp for variable I, then we expose this variable. So now our goal is just to analyze the first time that the partial derivative of our function evaluated at points sampled in this way become too large. And we want to show that the stopping time is at least 1 minus epsilon. Originally, we want to show the time is at least 1 minus epsilon times n, like in this 0, 1 unit, that's the right scale. And simply like notice that at time t here, we kind of, or we on expectation, should expose t times n variables. Okay. Okay, so next I'm going to show you the analysis step by step. So our goal is to analyze these partial derivatives of our function evaluated at points at time t. So we just write it this max quantity here on the left-hand side. And okay, we say, okay, this thing becomes too large. We are going to relax this maximum, the infinite norm, by a 2 plus eta norm, because we don't know which variable is maximum. So we just sum over all the variables and look at their partial derivative square times eta. You will see why we need this eta here. It's at least is very large. And next, we are just going to apply basically the Markov inequality for martingales. This is the next step. And finally, not finally, and the next step, we are going to apply a hypercontractivity inequality. So we switch from this 2 plus eta norm to 2 norm. Except here, what we are considering is random restrictions instead of the noise operator. So we need to prove something a little bit different, although it's kind of expected. That is, we show that if we have this kind of random restriction and we fix some time little t and time capital T, then the 2 plus eta norm evaluated at this point at time little t is upper bounded by the 2 norm of our function evaluated at time bigger t. So maybe let me expand it a little bit. So in a standard hypercontractivity inequality, what we have is on the left-hand side, you have your function applied with a noisy operator, and then you can take a higher norm and compare with the 2 norm. And here, what we are comparing is random restrictions with time little t before time capital T. So at beginning, you have no information about your input. And when you run your process a little bit, you expose a little bit more information about the inputs. So you can think of this Z little t as a noisy version of the Z capital T. So this is something you can expect to be true. And so we prove it. Okay. So now we are at this step where we use the hypercontractivity inequality to switch from the 2 plus eta norm to the 2 norm. And now we are show like why we need this eta. It's because we are going to take this plus eta 2 parts and bound it by the max influence, the individual influences. I mean, recall that the expected value of partial derivatives, the function at the endpoint is the influence. And if you consider t to be 0, it's a constant function. There's no influences. So this thing kind of interprets between 0 and the influences. So we expect that this value is less than the individual influence. This is this step, or maybe I should say this is a sub-martingale. That's a more easier explanation. And then what's left is this 2 norm. But we can now apply possibles inequality. In particular, here we are just summing all the variables and their partial derivatives squared. But to recall that at time t, we are already restricted, at least on average, t fraction of your inputs. So there are like 1 minus t fraction of inputs that is alive. So for those 1 minus t fraction of inputs, you can apply possible inequality. So the sum of partial derivative squares is bounded about by 1. And that's kind of only counting 1 minus t fraction of your inputs. So this is why you have this divided by 1 minus t here to get rid of this sum of the partial derivative squared. Okay. So at this point, you're basically done. It's because we know the max influence is small. Now all left to do is just to optimize with your parameters. Okay. I guess maybe it's better to stop, or I should use the Okay, maybe any questions at this point?
So this fact about restrictions being similar to noise, I guess it's something that people notice in the past, right? You can think of like you're picking which variable to stay alive, and then you're picking the value. It's a little bit like you're picking a noise parameter. By noise, because if you don't restrict it, then you apply noise.
Sorry. What did you say?
If I pick a variable to keep alive for BGP,
Yeah.
Sorry, to not keep alive probability.
Okay.
Then I pick a value at random, then it's like applying noise.
Oh, I mean the other way around, but when you fix more variable, it's like revealing more information about your inputs.
Okay, maybe I got it wrong with the P.
Yeah,
Maybe
maybe the direction is wrong, but
in any case, like restrictions and noise are very, very similar.
yes.
Looking at it from, say, like different perspectives.
Yes. So maybe you expect that you can just get this thing from the noise operator, from the standard activity. But unfortunately, we don't know how to do that, so we have to redo the proof.
So like maybe the absolute values is a little bit weird on the left-hand side.
That I don't think that's it. That's a reason. Yeah, but I don't know how to explain.
I have a feeling this could be derived without pre-proof. That's by observing.
No. I don't think the absolute value is, even if without the absolute value, I don't think it's true. Well, it does not imply directly. Maybe smarter way, but we didn't see how it's implied by the standard algorithm calculator inequality. It works. Yeah, maybe since we have time, maybe I just say a little bit, few words about how we bound the variance. So basically, so our idea is just to compare the entropy. Like, okay, if we are at, if we reach some random restriction, and then this is the entire Boolean cube of the random restriction, and this is what we kind of get, is the subset, which is a preimage of 1 for our function f. And we want to understand the size of this small ball. And we are going to basically analyze the KL divergence of our process. Anyway, if you don't know KL divergence, that's, for this case, it's just the log, the t minus the log of our size of this ball. So it tells you the number of, the fraction of ones in your input. Maybe, well, now I feel it's a bad idea to say anything. But anyway, so maybe because our random process is to expose the variable one by one, so it's kind of natural because it's kind of natural to analyze the KL divergence because of the chain rule. Yeah, so we just write on the KL divergence. We just write on the KL divergence and the conditioning on the random restrictions, kind of, and then we apply chain rule maybe, and use some fact about, like, in the end, if we stop our ball has density less than delta, and before the stopping time the density is actually greater than delta. And we also use like the level 1 inequality in some ways. Maybe I can talk more offline. And somehow it plays very nicely all together. So maybe that's it. Thank you.
Any questions for Pei?
So like about the hyperfunction.
Yeah. Sure.
So do you apply it, always apply it for probability equals to 1, like the last thing?
No.
No, you are.
Yes, so this capital T is actually also going to be a parameter. We're going to
Like,
choose.
could you show the last?
Okay.
How you
to-
apply it?
Yes.
Oh yeah. So you.
Yes. So this data will depend on the bigger T. And in reality, I think we set this bigger T to be a middle point between this little t and 1. And this is not interesting. It's just trying to optimize your bound.
Any more questions?
I think you can deduce it from the hyperconductivity theorem using the rich theorem interpolation.
So that may be true, but I don't know.
Yeah, like if you want to get hyperconductivity from 2 to P, you just use the jointness. Basically, it's like an operator, and then when you take, you compose it with its adjoint, you get back the noise operator. So you automatically get hyperconductivity from 2 to P, and then you can use, then you can interpolate and get hyperconductivity for other nodes.
Wait, what's I didn't get it.
So that you can look at it, consider the station operator, and look at the adjoint operator, and then compose them. Once you do this to look at standard noise operator, which you know is hyperconductive. This you get some hyperconductivity for the original operator. Once you get some hyperconductivity, you get some size of calculation.
Okay.
Yeah.
Oh, thank you.
Thank you for the question. Any other questions or comments? Okay, so let's thank Pei again.